So hi, today we will talk about multi-level inverters, but at first I would like to talk a couple of points we missed from the three-phase inverters. So as we discussed earlier, there has to be some dead time between the turn on and turn off of those top and bottom switches. Technically we cannot turn on these two switches simultaneously in a voltage source inverter, because if we do that, if we just turn on these things, we will short circuit our capacitor. But that doesn't mean we can turn on the other one at the instant that we turn off the other transistor. Why? Because there is a non-zero turn off time for transistors. So actually if we just ignore that thing, we can damage our transistor still, by short circuiting top and bottom switches. So in order to do that, we usually introduce some kind of dead time, that's also called blanking time, to prevent short circuits. And again, it totally depends on the properties of the transistors that we use, but it can be up to like 2-3 microseconds. And the idea is, this is normally our, control signal. So we are at that instant, we use a comparator. Okay, so that is our comparator, and this is our control signal. So at that instant, a switching state change will happen. So we will, let's say, turn off the top switch, and we will turn on the bottom switch. So normally they are like that, and instead of just applying the instantaneous turn on positions, what we do usually is delay the turn on time for, in this case it is the bottom switch. We delay the turn on time by delta t in this case, and we can achieve a period where both transistors are off. Okay. So similarly, during the next stage, so in that next one, so we are delaying the, again, like turn on point of the TA plus switch. So now I have again an off period, or a dead period, where both TA plus and TA negative is off. Okay. So this can be done either by some hardware components. Actually, this is just the definition of an XOR switch, so you can use that kind of latch circuits, or you can introduce those kind of systems in your embedded software as well. The effect of that thing is normally you are comparing your reference voltage with a triangular waveform, and you adjust your duty cycle accordingly. And if you are in the linear modulation range, you can say the PWM signal magnitude is linearly changes with the magnitude that I would like to give. However, that introduce some kind of loss portion. So instead of giving some positive voltage, we are giving some 0 voltage or negative voltage, whatever, depending on the PWM algorithm. But in the ideal case, that is what I would like to have, but I have some difference in both sides of that switching state. So that results in nonlinearity in the voltage output. So if your system is not that accurate, then maybe you can ignore that one. But however, if you want to get rid of that nonlinearity, maybe you can introduce some kind of correction algorithms, so you can estimate the portion that will be lost by that time. So you can try to give a slightly longer PWM signal. I mean, if you are interested, you can have a reading material in that one. Okay, so usually that portion, the ratio of that portion can be calculated by 2 times that time, because that's happening on both turn on and turn off states, and divided by TS and multiplied by VD is the reduction in your output voltage due to that time. As you can see, yes, having a longer dead time will cause more voltage drop, or similarly, if that time is happening more often, so that means if you use the same transistor but increase the switching frequency, okay, so that means you will shorten TS, so the ratio of that time will get larger. Okay, so those dead times will always reduce the output voltage magnitude with respect to current direction. So again, depending on the current direction, so if this is our ideal curve, so if current is larger than 0, so we will have a voltage drop in that curve, okay, like that. Or if our current is less than 0, okay, then we are having a voltage drop as well, so it has like that. So it is kind of, you can, mechanical analogy will be a friction force. Regardless of the rotation direction, the friction is always tries to reduce your speed, and that that time always tries to reduce your voltage level regardless of current direction. So maybe that figure will be more easy to understand. So that will be our ideal curve, what I would like to have. Okay, so if you are in the positive range, positive current, so you are having some reduction in your voltage, okay, then if your current changes direction, so that doesn't mean you will have smaller, that means the magnitude cannot be larger. So even in the negative voltage range, or negative voltage range, or in that peak, you will have a smaller voltage. So your output voltage with the duty cycle, you will have a distorted waveform like that. And actually, if you put it in your simulations to that time, you will be able to see that kind of distortions in your output signal. Okay, so the next topic that I would like to talk is the multi-level inverters. So multi-level inverters are again becoming more popular with applications like photovoltaic inverters, like HVDC converters, that kind of things. And they are commonly used in high power applications like in the megawatt or kilowatt ranges. So it can be used to increase output voltage capacity. So actually we have seen some examples in the first semester with the thyristor converters. So thyristors has quite a large rated voltages, but there can be some applications which require to give output voltages like even much larger than the maximum capacity of a largest thyristor. So we can use multi-level inverters as a way to increase our voltage levels without increasing stress on our transistors. And I will show a couple of topologies. Or another advantage for multi-level inverters are, instead of trying to generate a sinusoidal voltage, with normal PWM, actually I can divide that, sinusoidal into stacks. So you can get a much sinusoidal waveform which results in minimized harmonics and also minimized THDs, even if you have a low switching frequency. Okay, and as a side effect of that one, a lower harmonics, especially at higher frequency band, can help you to reduce EMI due to lower voltage steps. So let's start with a couple of definitions. Again, in this course, we are not really getting into details of the multi-level topologies, but I just want you to give a brief idea of how they work. And if you are interested, please have a look at the reading materials that I will supply. So in a two-level voltage source, so I would like to generate that sinusoids. So in that PWM algorithm, either I can give like VDC over 2 or minus VDC over 2. Okay, so I am adjusting two levels so that I can, if I take the first harmonic of that green line, I can have the dash sinusoid. So that means, so if I am getting into the maximum voltage of the sinusoid, I give some PWM with a higher on period and vice versa. Okay, so if you think of it, I can also, with different PWM algorithms, I can also have 3 level in that waveform. So I can give VDC over 2 0 volts minus VDC over 2, so I can have 3 level voltage source inverters. So in short, they are called 3LVSI, 3 level voltage source inverters. So the idea of the multi-level inverters lies in that, so instead of giving just VDC over 2, for example, in our case, can I find a topology which can give us like VDC over 2 or VDC over 4, and we will also have the 0 and minus V over 4 minus V over 2. So I have 1, 2, 3, 4, 5 levels. Okay, so this will be 5 level voltage output. Or similarly, you can divide it in even more sections. So you will have 1, 2, 3, 4, 5, 6, 7 voltage levels. Okay, so an analogy of that thing actually we are using in electrical machines, as you've seen in the last semester. Instead of using concentrated windings which generate like kind of square MMF waveforms, I can use distributed windings. Remember A1, A2, A3, short pitches, that kind of things. The idea is to put those square waves on top of each other to get a more stepped waveform that can simulate a sinusoid better. Okay, so let's start with HBridge inverters as a building block of multi-level inverters. So as you can see here, you can have a DC voltage source. So I have connected my load to the terminals here. So either I can give like VDC, or I can turn on those switches, so I can give minus VDC, or I can turn on these things or that ones to short circuit these two terminals, so I can have 0 volts. Okay, so using unipolar PWM algorithm, I can generate either VDC 0 or minus VDC, and I can adjust the pulse width modulation PWM duty cycle accordingly. So once you take the fundamental of that thing, you will have a sinusoid output. And what I can do next is I can add 2 of these HBridges in series. So maybe you have a photovoltaic panel. So the photovoltaic panel is connected to a DC source, and I have another photovoltaic panel, another DC source. So instead of connecting 2 photovoltaic panels in series and have a higher voltage, I can use like separate HBridges for those photovoltaic panels. So now I have different options. So you can maybe guess the voltage levels. Okay, I can either give positive voltage through here and positive voltage through that one to VDC, or I can have like positive voltage through that one and 0 voltage through that one, so I will have VDC, or I can give 0 voltage from both of them, I can have 0 volts, so on. So you can quickly calculate. I have 1, 2, 3, 4, 5 different options to generate the output voltage, and actually that can be the first voltage of the first HBridge. So itself is still working as a like 3-level inverter, just one of them, and I can adjust the PWM of the other one. So once I combine these two, okay, because V output is equal to V1 plus V2, they are connected in series, so the negative terminal of that one is connected to positive terminal of the second inverter. So once I add these two, I can have that kind of waveform. Of course, it doesn't have to be that kind of square wave. First of all, even if it is square wave, I can adjust those angles alpha 1, alpha 2 to eliminate some specific harmonics. So we have seen examples of that one, to eliminate fifth harmonic and so on. And secondly, again, they don't have to be like a square wave like that. I can still apply a PWM signal so I can estimate a smoother signal like that. Then I can increase like the number of series connected devices. So I can, here I have like 5, it's a photovoltaic panel, you can have 5 photovoltaic panels with 5 separate H bridges, and then you can obtain up to 5 times, okay, 5 times of each panel's voltage, and actually you can have the intermediate steps. So if you calculate that one, you can go from 5 VDC to 5 minus 5 VDC, and you will have 11 steps, and all those, you know, PWM signals can be adjusted. And the nice thing about that one, again, it doesn't have to be like photovoltaic panels, but that converter, okay, that converter or that switch just sees a voltage level with respect to that VDC voltage level. So for example, if you have, I don't know, if you have a switch that can withstand 1200 RPM, not RPM, sorry, 1200 volts, okay, so maybe your DC link voltage is at 1000 volts, so you are using barely enough voltage switches. So with that one, that DC voltage source can be 1000 volts, so at the output you can generate some voltage up to 5000 volts, okay, but then each switches in your H bridges can withstand only 1200 volts, okay. So that is the idea. You can either, you know, actually it has 2 advantages. Either you can make the voltage more sinusoidal, less THD, or you can achieve your THD targets with less switching frequency, or you can use multi-level topologies to go to higher voltages, you know, with available voltage ratings of your transistor switches, okay. So because even like you can have maybe 2000, 3000 3000 volts rated switches, but if you want to generate like tens of hundreds of thousand volts, so you need to use that kind of multi-level topologies. So again, here you can have, you know, different control techniques. Again, in this course, you know, that is outside of scope for this year. So calculation of the duty cycles, like what should be the ideal angles that you should switch the other one to get the best sinusoid shape. And there are many options on that one. But the simplest one, okay, the simplest one that we can discuss now is, instead of using, remember, in a normal 3-level HBridge controller, so you will have a carrier signal and you have a reference signal, and you compare these two and you just turn on switches on and off, okay. And if your reference signal is larger than your triangular, so you get into the overmodulation range, and the peak point or the maximum overmodulation is to just give a square wave. So we are doing more or less the same thing, okay. So if I had just used just for example single level, okay, a single H bridge, so if this is my carrier signal, this is my reference waveform, so it will just, for that waveform, it will just get into the overmodulation, then it will stay there, and I will not be able to generate the required waveform. What I do is, for each H bridge here, I just define a triangular a step higher and a step higher. So for the base, for example, in this one, our V1, the bottom is kind of our base signal. So that one sees a triangular waveform like that. So you compare the required voltage with that one. So it just turns on, it just turns off, so it will stay on for a long time, so it will stay on for a long time. And the next one is, you will have another PWM signal here. So the next one will just turn on, I don't know, somewhere here and turn off here. So it will generate the second base. So it will generate that second base. Okay. Then you can go like that. So you can define n many like triangular waveforms. Each of them is shifted by the voltage level that can be generated by the other H-bridges. And the last one, again, it is not shown here, but I think the frequency of the triangular is not realistic. Normally you have a much higher frequency, and again, it's not shown here. And the last one can generate some kind of PWM signals in the last stage, so you will have a much nicer voltage output. Okay, so the easiest way to generate PWM techniques is to generate different triangular waveforms with the same frequency but different offsets. Cool. So actually here you see a more realistic voltage output, and here we generate, I think it is 50 Hz signal, and our carrier is at 3 kHz. So 3 kHz normally not really high voltage frequency, but as we have like 5 H bridges, so I can generate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, I think 11 voltage levels. So even if your switching frequency is low, if you just calculate the THD of that curve, it will be really small. Cool. So similarly, this was for the sinusoidal PWM for the multi-level, and similarly we can apply a multi-level space vector PWM algorithm. And probably just a 2-level was quite confusing for you, but please don't get stuck with the details, but understand the main idea. So the main idea is, in a normal 3-phase inverter, I have 1, 2, 3, 5, 6 vectors and 2 zero vectors. So there are like 8 different combinations. So given a phasor, I can actually calculate which transistors to turn on and off. So I can calculate the ideal vector. In a more combinations, in a 3-level, 5-level combinations, so there are more voltage vectors. So that means if I want to generate the same phasor, I have like more vectors or more phasors, more switching states that I can use. So the idea is, so it is like a honeycomb structure with lots of triangles, and each of them again can be given a name. Here you see the d-axis and q-axis, the same, Park clock transformations, everything is same. Just how to generate that PWM signal stage is different. So again, instead of just using 8 vectors, I don't know how many vectors you have here, but this is you can define all those coordinates like 0, 0, 0, 1, 0, 0, 2, 0, 0. So again, you can think like XY axis. So you can give like 1, 2, 3, 4, 5 in series in that case, or you can have the other vectors as well. So in that phase vector, so you can turn on 1, 2, 3, 4, 5 vectors. So it is 0 for the first one, 5 for the second one, 0 for the third one as well. Or here you can have 2 from that phase, 2 from the other phase, etc. Again, I don't want to get into details, but there are some techniques like that. And another topology, again, just connecting series H bridges is not the only option. There are actually many different topologies, and just I would like to make a quite introduction. And another common topology is diode clamped multi-level inverters. So the idea is like that. So again, you can see the half bridge, like you can see normal HBridge structure as we have the VDC voltage. Okay, if you just look at those ones and those ones, and if you think those things as like single transistors, it seems like a normal HBridge. But instead of just connecting one transistor, I just connected two transistors on each place in series. So I have 1, 2, 3, 4, 5, 6, 7, 8 transistors. And another interesting point is, okay, it is just not two series transistors. I divided my DC voltage into half. Okay, so this is called the neutral point clamped. Okay, and PC neutral point clamped multi-level inverters. So I just divided the VDC into 2, so you can think this is VDC over 2, this is VDC over 2, and that point is connected to midpoints of transistors through diodes in that direction, and through here they just connected the medium points of transistors through that point. So we will see how that can be used. So first, I will just show you different combinations. So first, you can think it as a normal HBridge, so you can turn on these two transistors simultaneously, so both of them on or both of them are off. So if that top switches are on, the bottom switches will be off, vice versa. So if I just connect, I'm just showing you the half of that thing, so you can think what we are seeing is like the half bridge. So if you just turn on S1 and S2, and if you just turn off S3 and S4, so these are off, on. So let's have a look at, so this voltage comes here, so this is VDC, so this is like VDC over 2, so those diodes will be reverse bias, so they are off. So I have VDC volts here, comes to VDC here, and these are off. And again I have VDC over 2 here, this is VDC over 2, and that diodes again is like you can see here, VDC, and these two are reverse bias, so those diodes are off as well. So what I have is in that node I can connect it to VDC and generate VDC, and this is like half of the bridge. Of course I can do the same thing in the second leg, so I can generate 0 volts, so I will have VDC between phase terminals. So let's keep going in that single leg. So in that point I can connect it to VDC. Then I can do the conjugate of that one. I can turn off S1 and S2, and I can turn on S3, S4. So now that is connected to here, so that is 0 volts, and my diodes are still reverse bias, so the same thing happens like that. So this is VDC, okay, this is VDC, and that is reverse bias through here, that one is reverse bias through here, and the same thing happens on that one. We have VDC, so the diodes cannot conduct, so the bottom transistors actually make a connection to that neutral point, that 0 point, so I have 0 volts. So that's another voltage level. Then that's where things get interesting. So I can turn on S2, but I can turn off S1. The same things here, so they are like mirrored. So S2 is on, S3 is on. So if I have that, so I have no connection through here, okay, but that one actually has connected through here. Why? Because I have VDC over 2, okay, so if current is flowing in that direction, so remember that point I have this diode, So now it can flow through that way. Okay, if it flows through that direction, then that point will be VDC over 2. Or if the current is like, if the current is flowing through other direction, if the current would like to flow through here, okay, then if the current is coming through here, I have the S3 on, so it comes through here. S4 is off, so it cannot go below, so it will follow through that line. So for both positive and negative currents, I have a path, and if you follow that path, you will see my output voltage will be VDC over 2. So for that single bridge, I can generate VDC over 2 and 0. Okay, and actually you can do the, like, again, end of day disconnected through here, or you can add another bridge to have a 3-phase connection, and your load connections will be through those phases. So what you can do is you can generate 0 volts through here, and you can generate VDC over 2 here, so the load will see a minus VDC over 2, or it will see. So there are like 5 levels, right? VDC over 2, 0, minus VDC over 2, minus VDC. And again, you can generate even higher voltage levels. Again, here you have divided your source voltage into with three capacitors, and the idea is same. The idea is same. Instead of like connecting 2 transistors in series, now you have 3 transistors in series. It's like that. So I think you can work that it yourself, and application of that thing can be like, you don't have to have a large voltage source and divide it to capacitors. An application of that thing again can be a 5 photovoltaic panels, like each generating a low voltage. They are all connected in series. Yes, once you have a series VDC, maybe you can connect it using a normal HBridge. But what you can do is you can use a 5 not neutral point clamped voltage source inverter like that. Again, don't think that those panels can be just like single panels like 36-40 volts, but it can be many panels in series. So this can be easily in the order of several or hundreds of kilowatts, or in the megawatt range photovoltaic inverters. So now you have like 1, 2, 3, 4, 5 transistors in series, and you have 3 half bridges. So you have your connection through VA, VB, VC. Okay, so you can generate the required turn on and off sequences just at the right time to generate a really nice sinusoidal voltage out. And again, probably the finding the pattern is not that easy, I mean, even in that one, but if you just put all those things in a table, it is easier to see. In order to give the maximum voltage level 5 VDC, I need to turn on all the switches here on and all the switches off. So it is like HBridge. The bottom switch is off, top switches are on. Okay, so I will have the maximum voltage level. Then for the next voltage level for VDC, I need to turn off the highest switch. I need to turn off that one, so the remainings will be on. And for the temperate, I need to turn on that one. So I start with 1, 1, 1, 1, 1, 0, 0, 0, but then I bring it 1 down. Okay, so it became 0, 1, 1, 1, 1, 1, then the rest is 1. For 3 VDC, I switch my 1 states again and 1 right hand side. Okay, so maybe just take it to a rectangle, it can be easier to see. So next level, like that. And for 0 volts, then you came to the exact same position of that one. So depending on how many series high side transistors and how many series low side transistors that you have, you can generate all these voltage levels. And the nice thing about that one, even if you don't do the high frequency PWM switching, at each voltage level, the switching stage only changes in one of those things. Okay, SA5 becomes off, the rest is on, and SA5, as this becomes off, this becomes on, and the next one, SA4, becomes off, the complementer of that thing becomes on. So the switching losses of that thing can be minimized even if you have a really low THD levels at the outputs. Okay, so you only have a set of 5 switches on at any time, and the line-to-line voltage will be something like that. And again, as you can see, it is a much better waveform instead of trying to generate it with a 3-level voltage source inverter. And again, the voltage stresses in your transistors is reduced. Okay, so here I just wanted to make an introduction. So if you are interested in those topics, please have a look at the following links. And if you happen to work in a company that works in megawatt range or maybe hundreds of kilowatt range inverters, probably you will came across with multi-level inverters. Okay, thank you.